Hello, everyone. So I'm Laurent Ailleres from Monash University, and I'm going to present on LoopResources, and hopefully this will be a technology that will help reduce the mining footprint. So if we want a greener future, if we want our planet to survive, we need metals, and we need copper, and we need critical metals, and all the metals are required to make batteries and to carry electricity around the planet. So to do this, we have to extract metal out of the rocks, and we need to keep mining. So we need to change the way the public perceive mining, and we need to reduce the footprint of mines so that we can keep our license to operate and to do exploration and mining. So LoopResources is going to be a technology that we're going to develop in collaboration with industry to create more realistic digital twin of the geology or digital twin of the mine. We want to be able to optimize drilling from the first intersection, and we want to propagate and consider uncertainty throughout the entire life of a project, of an exploration project or mining project, and including throughout the property modeling process. So we can actually be more predictive in terms of characterizing all the properties within every cubic centimeters of the rock mass. We want to be able to characterize this in order to predict the geotechnical parameters, to predict the processing parameters, how much energy do we need to crush, what's the grade in that volume of rock, etc., etc. So this will increase the recovery rate and decrease the amount of energy and water required to extract the same amount, or maybe actually an increased amount of metal. So LoopResources will build on the Loop technology, which has been developed for the last 3 years. Loop is really a 3D modeling package, open source, that we have developed to allow decision makers to make quick decisions with respect to resources management. And we want those decisions to be tested quickly and modified, of course, accordingly if the risk or the interaction between different resources is too large. And so the Loop manager, the Loop project, is built around 3 pillars. There is a geological knowledge manager, which is developed by Mark Jessel and Boyan Broderick in the Geological Survey of Canada. Mark is from University of Western Australia, obviously. And what we do here is we're trying to extract automatically knowledge and information out of literature, and especially also out of maps, which is the Map to Loop software that Mark has been working on with Vitaly Ogarko at UWA. And it's a question of automating the input, or automating the augmentation of the data for input into our 3D modeling engine. And so our 3D modeling engine has been developed with Lachlan and myself at Monash University, and student Fernanda Alvarado as well, who's been working on intrusions. And basically it consisted in developing encoding structural geological rules in the modeling process. At the same time, Jérémy Giraud from UWA again has been working very hard on developing a new clever way to do geophysical inversions, including guided inversions, where the posteriori of the inversion of one data set is used as the a priori for the inversion of the next type of data set. For example, he's been using MT as a crude way to domain volumes, and then using that domaining, so the result of the MT inversions, as a domaining for gravity inversions, for example. And he has shown that you can get better results in terms of recovery of the basement topography, for example. Of course, throughout the entire workflow, we need to look at the uncertainty. So it's a separate pillar, but it's actually throughout the entire workflow. And the next iteration of Loop is going to look at Bayesian modeling. So we want to use all the parameters used for structural modeling. We want to use them. We want to make them part of an inference for geological and geophysical inversions. The ultimate aim is really to develop a singular likelihood functions for both geology and geophysics. So you may have seen this. We have developed proof of concepts where basically out of all the states in Australia, for some part of those states anyway, we are able to just draw automatically a rectangle on the map and press a button and get 3D models. Of course, you could do this almost everywhere in the world and you will get a model. The model is only significant if you actually know what you're putting in. So it's only in part of the world at the moment that the software works, but we have an automatic way to extract information from the geological maps and from outcrop bedding information, for example, to build those 3D models. And those 3D models are built in minutes, where it would have taken probably weeks in a more explicit or in a more classical way using other packages, commercial packages. So how do we do this? So this is the work of Map2Loop. This is the work of Mark Jessel. And basically it's trying to extract boundary between formations to also extract the topological relationship between fault formations and fault themselves. We're also estimating the thickness of the different packages and also trying to estimate or guesstimate the minimum offset on faults just from the map point of view. Of course, all these parameters, as I said, can then become part of a Bayesian inference. But that information is then fed into Loop Structural, which is a library developed at Monash by Lachlan in collaboration with myself, and you get a 3D model. So the Loop Structural is based on structural frames, and the structural frames are defined by the orientation of the finest train ellipsoid directions responsible for an event. So a fault is an event, another fault is another event, folding is obviously one event, and intrusions are also an event. So we can define those different directions. For example, for intrusions, there's direction of flows, there is the skeleton, and there is the normal to the skeleton, and we can just interpolate those different rectangular curvilinear coordinate systems throughout the entire volume to build our 3D models. So that means that at any points in space, we can actually calculate the distance between any point in space in the volume, in the model volume. We can calculate the distance between those points, which means we can do geostatistics within volumes that are defined by one structural frame. And of course, the way to build the models is combining the structural frame in a time-aware sense, so which means that one fault is applied at one time, and then you could have folding, and then you could have faulting again. But for the entire volume at the end, we have structural frames defining volumes within which we can calculate distances in all directions. So in all directions, in terms of the finest train or in terms of the structural frame, which means you can do geostatistics again within those volumes. So this opens the door, obviously, to being able to have geologically constrained geostatistical methods, which means that your ellipsoid is now following and conformable to the stratigraphy or conformable to the structural frame, conformable to folds. And you can actually do better estimations, so curvilinear geostatistics with better estimations of any properties. So those properties can be geotechnical parameters, they can be grades, and then you get a better resource model, or they could be so geotechnical, and also geometallurgical processes, geometallurgical properties. And you can then estimate roughly, you could then estimate, not roughly, you could then estimate, have a better estimations of the amount of energy required to crush the rock and whatever process is required for the extraction of metals. Yep. And so, for example, this is a work I did a long time ago in GOCAD, and just to illustrate what we want to do with the ellipsoid. So the ellipsoid is now conformable to the stratigraphic grid here in GOCAD, but there are some limitation in this package, and we want to be able to actually be able to calculate those ellipsoid in a recumbent fold, and they would have to be folded like this. So this is the anisotropy ellipsoid for here that shows that it's actually following the stratigraphical scalar field, if you want, or following the conformable shape to the horizon. So the distances for the geostats are calculated along the curvilinear coordinates. So to conclude, automation, yes, we want to automate the process from calculate input data. We want to automate the data input. We want to automate the 3D modeling package, the 3D modeling aspect of it, and then automate the property modeling for the entire workflow. And this is what LoopResources building on Loop technology is going to do. These are our core sponsors. So on the left here, you have the research organizations providing research input into the projects. In the middle, we have the Geological Survey of Australia, and including Geoscience Australia and the Geological Survey of Western Australia, providing cash and in-kind contribution to a current IRC linkage proposal. And on the right here, this is collaboration through MinEx, where we're getting also some support through Project 6. There is an empty space here because we're actually requiring funding from industry, and hopefully we'll have more logos in the future. Thank you very much.